Hello, this is John Miyares, and for the next two videos, we're going to introduce you to the concept of vectors. Now, vectors are another topic like polar graphs that we want to introduce you to in preparation for calculus, but in reality, they're not used at all in Calculus 1. You will see them at the tail end of Calculus 2, and they're spun all throughout Calculus 3, as another name for that course could be vector calculus. So why teach them at all in this class? Well, there's two reasons. First, they do tie together some different applications of trigonometry, and second, vectors are used a lot in physics. So if you plan on taking Physics 1 before you take Calculus 2, then you're going to need to know some of the basics of vectors. Now, this section of the text, unfortunately, is overloaded with content, which means that this video had the potential to be very, very long. However, what I decided to do was to split the videos for this lesson into two parts. The first part will focus on the basics of vectors, and the second part is going to tie together concepts of vectors with trigonometry and applications. Unfortunately for you, WebAssign Homework 9.1 will include problems from both parts of this video. So you're going to have to watch both of these lessons in order to make sure that you understand all of the material to be able to do the homework. On that note, let's get started. So what is a vector? A vector is a mathematical quantity defined by both magnitude and direction. Vectors distinguish themselves from plain old numbers, which we refer to as scalars. For example, there are two concepts that are often used to describe how fast something is traveling. Those are velocity and speed. Many people use these two terms interchangeably, but there is a subtle difference. When we're looking at velocity, we also want to consider what direction the object is traveling in addition to how fast it's going. Therefore, velocity is going to be a vector, and speed is going to be a scalar. Speed is just going to be a measure of how fast something is traveling, but does not have any particular direction associated with it. So that is why we distinguish it as a scalar separate from the vector, which will include both the speed and the direction something is traveling. Similarly, the distance that one can travel is measured as a scalar, but we can also define something called displacement, which is a vector. What is displacement? I guess it would be best to call displacement net distance traveled. Let's compare the two ideas. Suppose I told you I live 6 miles from my office in East Lansing. I leave in the morning, I get to work, I realize I forgot to bring my ID badge, so I travel 6 miles to get home, and then I travel 6 miles back to work. As far as distance goes, I have traveled 18 miles in my car. As far as displacement goes, I have traveled a net distance or a displacement of 6 miles from my house. Vectors can be represented graphically by directed line segments, which look like rays or arrows. The magnitude of the vector is represented by its length, while the direction of the vector is represented by the direction of the arrow. As far as labeling the parts of the vector, the arrowhead is called the head of the vector, while the far end without the arrow is called the tail of the vector. Two vectors are said to be equal or equivalent if they have the same magnitude and the same direction. It is important to note, though, that two equal or equivalent vectors do not have to be in the same location, and we'll talk about that in a minute. Vectors are labeled as equivalent with equal signs. So if we were to say that I have two vectors, which I'll call v and w, if they are equivalent, we would say v equals w. Here are some different ways we might interpret the two vectors geometrically. In picture A, we have vector v and vector w. They are considered equal because both vectors have the same magnitude, or the same length, and are pointed in the same direction. In picture B, vectors v and w have the same magnitude, but are pointed in different directions, so we could not say that they were equal. In picture C, vectors v and w have the same magnitude, but they are headed in opposite directions. We could call these vectors parallel, but we will not say that they are equal. Finally, in picture D, we see a case where vectors v and w are pointed in the same direction so that they are parallel, but they have different magnitudes. So they are not going to be equal. Vectors can be represented graphically by connecting 2 points in a Cartesian plane. Suppose we're given the following points as shown on the screen. Then let's say we are asked to plot the following points and to construct the following vectors: vector AB, vector CD, and vector EO. Then we might be asked to determine which vectors are going to be equal or equivalent to each other. The first thing we should do is plot the 6 points in question. The notation that's given here with the A and the B and the arrow on top implies that I want to start at point A and continue on towards point D. So my vector will start at A and continue this way. Similarly, for vector CD, I want to start at point C and continue to end at point D. And for EO, we will start at point E and continue to the end at point O, which is the origin. That's going to give us these 3 vectors you see here. Now let's look at our second question. Which of these vectors are going to be equivalent to each other? The 2 that look the closest are vector AB and vector EO. But in order to confirm that they have the same length and are headed in the same direction, we should look at their slopes. For vector AB, you're going down 1 and left 2, which is the same as vector EO, down 1, left 2. Now, I'm not going to actually calculate the length of the vector here, but it should be intuitively obvious that if going from the starting point to the ending point of the vector is a matter of going down 1 and left 2 in both cases, then those vectors must be equal. Meanwhile, if I look at vector CD, to get from point C to point D, you have to go down 2 and left 4, which will have the same slope as the other 2 vectors, but it will clearly not have the same magnitude. For vector AB, point A is called the initial point or tail of the vector. Point B is called the terminal point or the head of the vector. This notation with the A and the B and the arrow on top is read as vector AB, although the text will refer to vectors also with these bold-faced letters such as a U or a V. So for example, we could mark vector AB with a bold-faced U. We could also mark vector CD with a bold-faced V and vector EO with a bold-faced W. Using these notations will help us clean up our work with vectors so we're not going to always be tied to the Cartesian coordinate plane. in this case, if we were asked which vectors were equal to each other, we don't have to say vector AB is equal to vector EO. We could just say vector U is equal to vector W. The length of a vector, or its magnitude, is expressed using absolute value notation. So we could write what looks like the absolute value of vector AB or the absolute value of vector U. We would calculate the length of this vector or its magnitude by using the distance formula. And when I say the distance formula, it's essentially a variation on the Pythagorean theorem where instead of computing a squared plus b squared equals c squared, you're looking at the change in x squared plus the change in y squared will equal the length of that diagonal squared. Formula-wise, you're taking the difference in the two x values squared and the difference in the two y values squared, summing them up, and taking the square root of the result. For example, say I asked you to find the magnitude of vectors u and v in this diagram. If we were to apply the distance formula for vector u, we would take the difference in the two x's, -2 minus -4, then square that, plus the difference in the y's, 5 minus 4, squared. Simplifying, we see this -2 minus -4 comes out to +2, and 5 minus 4 equals 1. So squaring the 2 and the 1 will get you 4 plus 1 under the radical sign, which equals 5. So the magnitude of vector u will be the square root of 5. Finding the magnitude of vector v will be similar. Why don't you pause this video for a bit and try to do that one on your own? For vector v, applying the distance formula would be again a matter of computing the change in x, which will be 3 minus -1, and the change in y, which would be 1 minus -1. Simplifying inside the parentheses, 3 minus -1 is 4, and 1 minus -1 is 2. Squaring and summing each of those pieces under the radical sign gets us the square root of 16 plus 4, which simplifies to the square root of 20, which further can simplify as 2 times the square root of 5. A vector v is considered to be in standard position if its initial point is the origin in an xy coordinate system, and its terminal point is some other location which we'll call the point A, B. Here is an example of this. The two vectors that you see here are equal vectors. Going from the initial point to the terminal point, you're going right 5 and down 4. The blue vector is considered to be in standard position because the tail is at the origin. Now, to avoid confusion between points and vectors, we're going to introduce a new notation here to describe a vector. And that's going to be with these things that look like giant less than signs and greater than signs. These grouping symbols are called angle brackets, and this notation where I have v equals a comma b inside the angle brackets is called component form. The way we will interpret this is that the first value, the A, is going to be the change in X from our starting point, or the left-right shift, while the value of B is going to be the change in Y, or the up-down shift from our starting point. In this case, since the vector is going right 5 and down 4 from the origin, we're going to label this vector with the quantity inside the angle brackets as 5, comma, -4. In this notation, the A value, which here equals 5, is called the horizontal component of the vector, while the B value, which in this problem is -4, is called the vertical component of the vector. Let's look at an example of this. Suppose I was given 2 points. Point P has coordinates -1, 6, and point Q has coordinates -3, 2. Let's say you're asked to sketch vector U, which could also be as vector PQ, and then to express vector U in component form. Maybe you should pause this video to see if you can do this one on your own before we continue. So the points to be plotted are going to be both in quadrant 2. Point P is left 1 up 6, and point Q is left 3 up 2. Vector PQ geometrically is going to start at point P and terminate at point Q. As far as component form, to get from point P to point Q, you have to travel left 2 and down 4. So in component form, we would put inside the angle brackets -2, -4. Now let's say we want to sketch vector U in standard position. Take a minute on your own to give this one a try as well. For the vector to be in standard position, it must start at the origin and then must end 2 units to the left and 4 units down, which would place the terminal point at the coordinates -2, -4. From here, we'll connect those 2 points with an arrow. Now, what if we said we want to sketch a vector equivalent to U that has an initial point with coordinates 4, 3, and we also would want to know where the terminal point would be? Pause this video one more time to see if you can come up with this one on your own as well. Here's the point 4, 3. In order for the vector to be equivalent to the other two, you'd have to go left 2 and down 4, which would put you down here at the point 2, -1. Once there, we can connect the 2 points with a directed line segment or arrow. Now we have these 3 vectors that are all equivalent to each other, that all have the same magnitude, they all have the same direction, but they just have different initial points. The blue vector is in standard position because it starts at the origin, but otherwise these vectors are all going to be considered equal or equivalent. If you are given a vector in component form and you want to find its length or its magnitude, all you would have to do is take the sum of the square of the components and then take the square root of the result. After all, the components here represent the change in x and the change in y as you go from the initial point to the terminal point of the vector. So then, finding the length of this diagonal vector will follow the Pythagorean theorem pattern as before. For this particular example, if you were asked to find the length of vector u, or the length of vector PQ, we could apply this formula and insert each of the components in its place. Negative 2 squared is 4, and negative 4 squared is 16. When we add those up, we will end up with a 20 under the square root sign. So the magnitude, or the length of this vector u, will be the square root of 20, which can be further simplified as 2 times the square root of 5. Let's talk about operations on vectors. Suppose vectors u and v are written in component form, and I'll introduce this value k to be any real number. Now, when I say component form, I'm basically saying that vector u is going to look like it has horizontal component u1 and vertical component u2 inside the angle brackets, while vector v I will label here as having horizontal component v1 and vertical component v2. So it will be v1 comma v2 inside these angle brackets. The scalar product of k and vector v can be labeled as kv, which is going to be evaluated by simply multiplying the constant k by each of the components. So the components of vector kv will be k times v1, comma, k times v2. They call this a scalar product because essentially you're just changing the length of the vector by some scaling factor. For example, if k equals 2, then you're doubling the length of the vector. If k equals 3, you're tripling it. If k equals 1/2, you're cutting the length of the vector in half without actually changing its direction. We can also say that k times v is a scalar multiple of v. Now, if we wanted to add two vectors together, vector u plus vector v, all we would need to do is add their components together. So I have u1 plus v1, comma, u2 plus v2 inside the angle brackets. Essentially, we're combining the horizontal movements together and the vertical movements together. If you see a minus sign in front of a vector, what you're essentially doing is having that vector travel in the opposite direction of the original vector. So you're multiplying each of the components of the vector by -1. So if vector v had components v1 and v2, vector negative v would have components negative v1 and negative v2. Finally, if we wanted to subtract two vectors, vector u and vector v, you could just subtract the corresponding components as shown here. Let's look at how we might do some operations on vectors in this form. Suppose we are given the following vectors. U equals 5 comma -2 inside the angle brackets, and v equals 3 comma -4 inside those angle brackets. And we are asked to evaluate the following. We want to know the sum of vectors u and v, the sum of vectors -3u and 4v, the length or the magnitude of u plus v, and the length or the magnitude of -3u plus 4v. The sum of u and v is a matter of adding the components together, meaning you have 5 plus 3 as the new horizontal component and -2 plus -4 as the vertical component. This simplifies to the vector 8, -6 inside the angle brackets. Now let's think about what's happening. You're combining an action in your first vector where you're going right 5, then down 2, with a second vector that is going right 3 and down 4. Thinking about it geometrically in your head, the net result will be ending up going right 8 and down 6. Now let's look at the second example. If we've got -3u plus 4v, we want to multiply each of the components of each vector by that scalar coefficient before adding them together. Distributing -3 times the vector u will give you -15, 6 inside the angle brackets, and 4 times vector v becomes 12, -16 inside the angle brackets. Combining the corresponding components gets us a horizontal component of -3 coming from -15 plus 12, and a vertical component of -10, which comes from 6 plus -16. Now let's find the length or the magnitude of each of these new vectors. For the vector u plus v, we'll take the square root of the sum of the squares of these components. So under the radical, we'll have 8 squared plus -6 squared, which expands out to 64 plus 36 under the radical sign, which will become the square root of 100, or 10. So the length of vector u plus v is 10. Similarly, the length of vector -3u plus 4v will be computed by taking the square root of the -3 squared plus 10 squared. Those pieces expand to 9 plus 100, which combine to the square root of 109 as our final answer. What does the addition of vectors look like geometrically? Well, the sum of two vectors u plus v is represented by the directed line segment from the initial point of vector u to the terminal point of vector v. Graphically, we can look at this in one of two different ways. Option 1 is called the triangle method or the head to tail method. We would first place the vectors with the head of the previous vector connected to the tail of the second vector we want to add to it. Remember, it's okay to move these vectors to where we need them because vectors define magnitude and direction, not location. When we do this, the resultant vector u plus v will be formed by connecting the tail of the first vector to the head of the second vector. We also have what's referred to as the parallelogram method, where we place both vectors that are being added at the same initial point. And typically, if the vectors are in standard position, that point is going to be the origin. We're going to use those two vectors to form two adjacent sides of a parallelogram and then make a copy of those vectors to form the remaining two sides of that parallelogram. The diagonal of the parallelogram that has its initial point at the same location as the other two vectors will be the sum of those two desired vectors. Let's tie this back to the example we just did before this slide. Suppose you're being asked to sketch the following vectors and determine their sum, where u was the vector 5, comma, negative 2, and v was the vector 3, comma, negative 4. Let's start by graphing these two vectors separately in standard position. The vector 5, comma, negative 2 will start at the origin, then go right 5 and down 2 to end at the point 5, comma, negative 2. The other vector 3, comma, negative 4 is shown here in blue, going right 3 and down 4 from the origin. What I'm going to do next is make a copy of vector v in such a way that its tail is going to start at the head of where vector u is. I've drawn this dash line in blue, and you'll see it maintains the same direction and magnitude of vector v. So I'm going right 3, down 4 from the head of vector u. Notice that the point where this ends up is 8, comma, negative 6. Now, we could have added in the other direction, made it vector v plus vector u, and made a copy of this vector u to start at the head of vector v. Then from here, we would go over 5 and down 2, which still places us at the point 8, comma, negative 6. The sum of u and v could be represented by this green vector that starts at the point 0, 0 and continues to the point 8, negative 6. So in fact, we see all the ways to put this together. We see the parallelogram formed, as well as this diagonal that is coming across from it, but we also see the two different triangles that are created by placing the tail of one vector at the head of the other. This seems to be consistent with what we did earlier when we just added the corresponding components of each vector. What I'm hoping you see here is that we can look at the sum of two vectors either algebraically by adding the various components, or geometrically by physically taking these arrows, which represent the vectors themselves, and attaching them to each other from the head of one to the tail of the next one. This geometric approach will be helpful as we work our way towards the next video and begin exploring applications of vectors. Here is a slight variation on the previous example. Suppose you're given two vectors. You're not told their components, but you are told that the magnitude of vector u is 5 and the magnitude of vector v is 4. Also, you're told the angle between vectors u and v is 120 degrees. Now suppose you are asked to find the magnitude of the vector represented by the sum of vectors u and v, as well as the angle that the new vector u plus v will make with vector u. Because we're not given specific components, horizontal or vertical, we're going to just have to draw out something that will represent this situation the best way that we can. To simplify matters, let's just say that vector u will be this red vector I've drawn here that has a length of 5 that's just going to follow the positive x-axis. Since we're not told a specific direction that this vector goes in, I can pretty much place it wherever I want. We don't know the components of vector v either, but we do know that the angle between vectors u and v is 120 degrees. So I'm going to draw this blue vector v with a magnitude of 4 in quadrant 2 that will be a 120 degree rotation from vector u. Since I'm not given the components of the vectors, the only way I can add them is through one of the graphical methods. So I'm going to make copies of both vector u and vector v here to form a parallelogram as shown. The diagonal of this parallelogram, starting from the origin and graphed here in green, will represent the vector u plus v. Again, I don't know what the components of vector u and vector v are, but I'm also not asked to find them either. What we are asked for is the magnitude of this green vector and the angle that it forms with vector u, which I'm going to mark here with angle theta. Looking at what we do know, we've got two sides of the parallelogram, with side u equaling 5 and side v equaling 4. I know there's a 120-degree angle between vectors u and v here at the origin. What we cannot assume is that the green vector is going to split that 120-degree angle in half. What is safe to assume, however, is that since we have a parallelogram, that this angle here in the right corner is going to be 60 degrees because the two successive angles in any parallelogram must add up to 180 degrees. Now, with this information, I have a triangle over here with side u equals 5, side v equals 4, and the angle created by these two line segments is going to be 60 degrees. With that, we could use the law of cosines to find the length of the green vector u plus v. Let's use the formula c squared equals a squared plus b squared minus 2ab cosine angle c, treating side A as length 5, side B as length 4, and angle C as being measured 60 degrees. Evaluating each piece of this gives us 5 squared, which is 25, 4 squared, which is 16, and the cosine of 60 degrees is 1/2. Multiplying and combining the numbers together here will give us 41 minus 20, which is just 21. That will make the magnitude of vector u plus v the square root of 21. Now we still need to find the measure of angle theta, which is the angle between this green vector u plus v and the red vector u. For that, we're going to have to use the law of sines. We now have the lengths of all three sides of the triangle, and we have the 60-degree angle in the corner, so we can say that the sine of angle theta over its opposite side, which is 4, equals the sine of 60 degrees over its opposite side, the square root of 21. Cross-multiplying, then dividing by the square root of 21 in order to isolate the sine of theta gives us sine of theta equals 4 times the sine of 60 degrees divided by the square root of 21. Decimalizing that gives the sine of theta to be approximately 0.755929. So angle theta will be the inverse sine of that, which comes out to approximately 49.1 degrees. I'm not going to worry about any potential obtuse solution because clearly from the picture, angle theta has to be acute. Additionally, the only way angle theta could be obtuse would be if the opposite side, of length 4, was the longest side in the triangle, which clearly it is not. We've got a couple of more concepts to introduce before we end this video. The first one is something called a unit vector. A unit vector is a vector with a magnitude or a length of 1. For example, the vector square root of 3 over 2 comma 1/2 inside the angle brackets is a unit vector. And we can verify this by applying the Pythagorean theorem. If you square each component, you'll get 3/4 plus 1/4, which adds up to 1. So long as the sum of the squares of the components of the vector equals 1, you'll have a unit vector. Now, one of the questions you're going to see on the homework might look like this. Find a unit vector that has the same direction as vector 3, 4. This might make more sense if we try to visualize this problem graphically. Here's a graph of the vector 3, 4 in standard position. It starts at the origin and continues outward to the point 3, 4. The magnitude of this vector can be computed by using the distance formula or the Pythagorean theorem, then taking their square roots. 3 squared is 9, 4 squared is 16. That will add up to 25 under the radical sign, so the magnitude or the length of this vector is 5. What we're interested in now is a vector that has length 1, but has the same direction as this blue vector here that has length 5. So graphically, what we're looking for is this red vector here. If we can figure out where the terminal point of that red vector should be to make it have a length of 1 instead of a length of 5, then we've solved our problem. Here's the deal. We essentially need to scale this vector back. So since the vector 3, 4 has a magnitude or a length of 5, and what we want is to have a vector that has a length of 1, then we'll just multiply everything by 1/5, or divide each of those components by 5, which will give us the vector 3/5, 4/5 inside the angle brackets. Applying the Pythagorean theorem, we should easily see that this vector will have a length of 1. The last thing we're going to introduce in this presentation is a notation to describe special unit vectors. We're going to define vector I as a horizontal unit vector. So the components inside the angle brackets will look like 1, 0. Vector J will be a vertical unit vector. So its components are going to be 0, 1 inside the angle brackets. Based on these, any vector can be expressed as a linear combination of unit vectors I and j. Well, what does that mean? Let's look at a few examples. If I was given the vector 5, 2, which has horizontal component 5 and vertical component 2, we can write this vector as 5i plus 2j, because vector I, being the vector 1, 0, will give you 5, 0 after you multiply 5 by the I. Similarly, 2j is the same as 2 times the vector 0, 1, which becomes 0, 2. Adding those definitely will get you the vector 5, 2. Here's a second example. The vector 3, -4 will translate as using the unit vectors 3i minus 4j. 3i, remember, is really the vector 3, 0, and -4i will translate as 0, comma, -4. When we add these together, the zeros aren't going to really do anything, so that will become 3, comma, -4. We can also do this backwards. Suppose we have the vector w equals -2i plus 3j. Knowing that vector I is a unit vector 1, comma, 0, and vector j is the unit vector 0, comma, 1, then -2i plus 3j can turn into the vector -2, comma, 3. Now, we can also add or subtract vectors in this form. It would just be a matter of applying the basic rules of algebra and simplifying expressions as though we were just combining like terms. For example, suppose we wanted to add two vectors u and v together. If we have vector u written as 5i plus 2j and vector v written as 3i minus 4j, we can regroup our like terms and combine them to get 8i minus 2j as our final answer. Similarly, let's say we wanted to subtract 3u minus 2w. Well, 3u would be a matter of multiplying 3 times the vector 5i plus 2j. Then the minus 2 times w would be a matter of subtracting 2 times the vector -2i plus 3j. Distributing there will give us 15i plus 6j plus 4i minus 6j. Combining together the like terms will give us 19i plus 0j, which, since 0 times anything equals 0, we could simplify this expression as just 19i. So I'm going to stop here before continuing because I think this was enough information to try to absorb in one lesson video. What I would recommend is to go ahead and try these problems here in this problem challenge before going on to the second half of this assignment, where we will look at various applications of vectors and really try tying things back to trigonometry. As always, if you have any questions, feel free to send me an email or post your questions on the discussion board. Thanks for watching, and we'll see you all soon.